In this lecture of organic chemistry for B.Sc. first semester classes, we will study about methods of formation of alkanes. First method is catalytic hydrogenation of unsaturated hydrocarbon. The addition of hydrogen to unsaturated hydrocarbon like alkene or alkyne to form alkane is called hydrogenation. In this reaction, unsaturated compound is treated with molecular hydrogen in presence of finely divided metal catalyst like platinum, palladium or Raney nickel. With these catalysts, reaction proceeds smoothly and quantitatively at ordinary temperature and pressure. Raney nickel required for this reaction can be prepared by dissolving nickel aluminium alloy in sodium hydroxide. The alkane can also be prepared from unsaturated hydrocarbon using ordinary nickel but at higher temperature of about 523 to 573 Kelvin. The reaction is known as Sabatier-Sanders reaction. Catalytic hydrogenation is most important method for preparation of alkane. However, we cannot prepare methane by this method. Example of Sabatier and Sanders reaction: ethylene on reaction with hydrogen with nickel at 523 to 573 Kelvin form ethane, and acetylene under similar condition form also ethane. Second method of formation of alkane is reduction of alkyl halide. Alkane can be prepared by reduction of alkyl halide with different type of reagent by using direct or indirect reduction method. First we study about direct reduction of alkyl halide. Direct reduction of alkyl halide can be done in different ways. Number 1, alkyl halide can be reduced to alkane by reduction with metal such as zinc in presence of acetic acid or HCl, zinc in presence of sodium hydroxide, or using zinc copper couple with ethanol. For example, true bromobutane on reduction with zinc HCl produce butane and HBr. Second direct reduction method is reduction of alkyl halide with chemical reagent like lithium aluminum hydride and sodium borohydride. We can also use triphenyl tin hydride to reduce alkyl halide into alkane. Lithium aluminum hydride can reduce easily primary and secondary alkyl halide to alkane, but tertiary alkyl halide undergo dehydrohalogenation to give alkene. For example, if we reduce ethyl chloride with lithium aluminum hydride, it will form ethane. But if we try to reduce tertiary alkyl halide like tertiary butyl chloride, then it will undergo dehydrohalogenation to form corresponding alkene. Sodium borohydride reduces secondary and tertiary alkyl halide but not primary halide. Whereas triphenyl tin can be used to reduce all the three type of alkyl halide into alkane. Alkyl halide reduces to alkane with lithium aluminum hydride, sodium borohydride, and triphenyltin hydride. In their reduction, lithium aluminum hydride, sodium borohydride, and triphenyltin hydride provide hydride ion, which will replace halide ion from alkyl halide as shown in figure to form alkane. Next is catalytic hydrogenolysis. Catalytic hydrogenolysis means cleavage of sigma bond with hydrogen in presence of a catalyst. Palladium in presence of carbon is the best catalyst for this reaction, but Rani nickel can also be used for this method effectively if it is used in excess amount. Next method of reduction is reduction with Hi and red phosphorus. Alkyl iodide react with concentrated Hi solution in presence of red phosphorus at 423 Kelvin to form alkane plus I2. The function of red phosphorus in this reaction is to remove liberated iodine in the reaction by reacting with this according to the given equation. Phosphorus plus iodine form phosphorus triiodide. This will prevent iodine to react back with alkane to give alkyl halide. Next reduction type of alkyl halide is indirect reduction. In indirect reduction of alkyl halide to form alkane, alkyl halide react with magnesium and dry ether to form alkyl magnesium halide called Grignard reagent. The Grignard reagent is very reactive and hence decomposed by water or any other potential proton donor such as alcohols and amines to form alkane. For example, CH3CH2 MgI, which is a Grignard reagent, react with water to form CH3CH3, that is ethane, and MgOHI, hydroxy magnesium iodide. Next method is Wurz reaction. Wurz reaction involve reaction of two molecules of same or different alkyl halide with metallic sodium in presence of dry ether to form alkane. The order of reactivity of different alkyl halide in this reaction is: alkyl iodide is more reactive than alkyl bromide is more reactive than alkyl chloride. One thing is to be noted here: alkyl fluoride do not react in Wurz reaction. This method is useful for preparation of symmetrical alkane, that is, alkane containing even number of carbon atom such as ethane, butane. However, this method is not suitable for preparation of unsymmetrical alkane. Unsymmetrical alkane means alkane which has odd number of carbon atoms such as pentane, heptane. The reason being that the preparation of odd alkane require reaction of equimolar mixture of two different alkyl halide with sodium. These two different alkyl halide used in this reaction, in addition to reacting with each other, also react amongst themselves. That is, for example, if we use a mixture of methyl bromide and ethyl bromide to form propane with sodium, it form a mixture of ethane, butane and propane according to the reaction shown in figure. Methyl bromide react with another molecule of methyl bromide with sodium to form ethane. Ethyl bromide react with other molecule of ethyl bromide and form and butane. Ethyl bromide react with methyl bromide to form propane. And in this way, we see that from the example, in addition to propane, there will also form ethane and butane. The boiling point of these alkanes are very close. Hence, they cannot be easily separated in laboratory. That's why this method is not used to prepare odd number of alkane, that is unsymmetrical alkane. Limitation of Wurtz reaction. Halogen compound containing other functional groups such as alcohol and carboxylic acid cannot be used in this reaction because these functional groups such as OH, COH can interfere with the reaction of halogen in presence of dry ether with sodium. For, for example, alcohol react with sodium to form sodium ethoxide. Carboxylic acid group changes into sodium salt of carboxylic acid, and in this way they will interfere with the reaction of halogen compounds. This reaction fails with tertiary alkyl halide because tertiary alkyl halide undergo dehydrohalogenation to form alkene. This reaction cannot be used to prepare methane. Importance of this reaction. It is a very useful reaction for ascending the series of organic compound. That is, to increase the number of carbon atom in a given molecule. This method can be used because this method involves formation of new carbon-carbon bond. Now we will discuss the mechanism of Wurtz reaction. The reaction is believed to occur by two types of mechanism. First mechanism is through the intermediate formation of organosodium compound. The organosodium compound formation mechanism is operate when reaction is carried out in solution. In this mechanism, alkyl halide react with sodium to form alkyl sodium. This alkyl sodium then react with alkyl halide by SN2 mechanism to form alkane and sodium halide. The evidence in the support of this method are this reaction, like any other organic reaction, gives side product. For example, when two molecules of ethyl iodide are reacted with sodium in presence of dry ether, we obtained butane, but we also obtained ethane and ethylene in this reaction as byproduct. The formation of these byproduct or side product can be explained in terms of the mechanism we given above. For example, CH3CH2I react with sodium to form CH3CH2 negative and Na positive, that is ethyl sodium. This ethyl sodium then react with ethyl iodide by the mechanism shown in the diagram to form ethane and ethylene. Second mechanism is free radical mechanism. The free radical mechanism operate when the reaction is carried out in vapor phase. In this mechanism, sodium first react with alkyl halide forming free radical, and this free radical then couple together to form alkane. As shown in diagram, alkyl halide react with sodium to form alkyl radical and sodium halide. This alkyl radical then combine with another alkyl radical to form alkane. The byproduct formed in this reaction can are also explained by using this free radical mechanism as discussed in diagram. CH3CH2I react with sodium to form ethyl free radical. This ethyl free radical then react with ethane and undergo disproportionation, that is, simultaneous reduction and oxidation takes place. In this step, ethyl radical will abstract hydrogen radical from the alkane, that is ethane, as shown in figure, to form ethane and ethylene. From this mechanism, we have to note one thing. During the movement of single electron, we show the movement of electron by half-headed curved arrow. Next method for preparation of alkane is Core-House reaction. In Core-House reaction, alkyl halide react with lithium dialkyl cuprate, which is also known as Gilman reagent, to form alkane. R2CuLi, lithium dialkyl cuprate, react with alkyl halide in presence of dry ether or tetrahydrofuran to form alkane organocopper compound and lithium halide. Lithium dialkyl cuprate needed for this reaction is itself prepared from alkyl halide by following way. Alkyl halide react with lithium in presence of ether to form organolithium compound. This organolithium compound then react with CuI to form dialkyl cuprate compound of lithium. For good yield, alkyl halide used in this reaction are either methyl halide or primary alkyl halide or secondary cycloalkyl halide. While the methyl group in organometallic compound may be methyl, primary, secondary or tertiary. As shown in the diagram, to convert methyl iodide into N-pentane, first we reacted methyl iodide with lithium in presence of ether, then methyl iodide is converted into methyl lithium. This methyl lithium then react with lithium iodide, copper cuprous iodide to form lithium dimethyl cuprate. This lithium dimethyl cuprate have one carbon atom and we have to convert it into pentane. So now we will treat this compound with alkyl halide having 4 carbon atom, that is butyl iodide. This butyl iodide reacted with this lithium dimethyl cuprate to form N-pentane. In second example, we convert secondary butyl chloride into 3-methyl octane. Secondary butyl chloride have 4 carbon atoms and 3-methyl octane have 8 carbon atom. To convert secondary butyl chloride into 3-methyl octane, we treat it with lithium in presence of ether. Then secondary butyl chloride will form secondary butyl lithium. This secondary butyl lithium then treated with CuI and it will form lithium disecondary butyl cuprate. Now we will see the structure of 3-methyl octane so that we can predict about the structure of alkyl halide. From the structure of dialkyl lithium cuprate and 3-methyl octane, we see that the alkyl group which is added to lithium disecondary butyl cuprate from alkyl halide will contain 5 carbon atom in straight chain. That is, alkyl halide used in this case is 1-bromopentane. This 1-bromopentane react with lithium disecondary butyl cuprate to form 3-methyl octane. Here, one thing is to be noted: we cannot use branch chain alkyl halide instead of branch chain lithium dialkyl cuprate, because if we use branch chain alkyl halide, then this will undergo dehydrohalogenation to form alkene. Merit of this reaction is better than Wurtz reaction because it can be used to prepare all type of alkane like straight chain alkane, branch chain alkane, alkane containing even number of carbon atom or odd number of carbon atom. This is a useful reaction for the synthesis of higher alkane. Next method for preparation of alkane is decarboxylation of carboxylic acid. The decarboxylation reaction involves the removal of carbon dioxide from carboxylic acid. In this reaction, when sodium salt of monocarboxylic acid is fused with soda lime, a molecule of carbon dioxide is lost and alkane with one carbon atom less than the carboxylic acid is formed. For example, sodium acetate react with sodium hydroxide and CaO at 630 Kelvin temperature to form sodium carbonate, and the alkane form has formula CH4 which has one carbon atom less than sodium acetate. Instead of sodium salt, carboxylic acid directly can be used in this reaction. That is, we can use acetic acid in place of sodium acetate, which react with sodium hydroxide and CaO, that is soda lime, mixture of sodium hydroxide and quicklime in the ratio 3:1 at 630 Kelvin to form methane, sodium carbonate and water. Sodium hydroxide alone could also be used in this reaction, but we use soda lime in this reaction due to following two reasons. First, it allows the reaction to be carried out at relatively higher temperature so that there will be complete decarboxylation in the reaction. Second, quicklime present in soda lime keep the reaction mixture dry, because we know that sodium hydroxide is a hygroscopic compound. Mechanism of this reaction is as follow. In this reaction, hydroxide ion attack the carbon atom of carboxylate anion as shown in the figure, followed by removal of alkyl group from the intermediate form to give alkyl anion and hydrogen carbonate. This alkyl anion then abstract hydrogen from hydrogen carbonate to form alkane and carbonate ion. Limitation of this method is that in this method only sodium acetate will give good yield of methane, while in all other cases such as decomposition of sodium propanoate or sodium butyrate, a mixture of product is obtained. For example, if sodium propanoate is undergo decarboxylation reaction in presence of soda lime, it will give ethane, methane, hydrogen plus unsaturated hydrocarbon. So we will see from the reaction there is a lot of product formed in this reaction. Next method is coal-based electrolytic method. In this method, a concentrated aqueous solution of sodium or potassium salt of fatty acid is electrolyzed to form alkane. For example, sodium acetate on electrolysis will form ethane, sodium hydroxide, hydrogen and carbon dioxide. Electrolysis means breaking of bond by the passage of electricity. This reaction is occur via following steps. As we know that sodium salt of carboxylic acid is a strong electrolyte, so its aqueous solution undergo ionization to form so acetate anion plus sodium ion. Similarly, water is also ionized on passing electricity, but it is a weak electrolyte, hence it ionized to smaller extent than that of sodium acetate, which is a strong electrolyte. In case of water, the ion formed are hydroxide ion and hydrogen ion. These different type of ion formed during electrolysis then migrate towards the respective electrode, or we can say these ion will move towards oppositely charged electrode. Acetate anion and hydroxide ion are negatively charged and they will move towards anode. At anode, acetate anion, which has higher electron releasing tendency than that of hydroxide ion, will be discharged according to the reaction shown in diagram to form ethane and carbon dioxide, while sodium ion and hydrogen ion, which are positively charged, they will move towards cathode. At cathode, they will undergo reduction because the electron accepting tendency of hydrogen ion is much higher than that of sodium ion. Therefore, hydrogen ion will be discharged in preference to sodium ion. According to the reaction shown in figure, hydrogen ion accept two electrons that are produced at anode during oxidation of acetate anion to form hydrogen atom, which then combine to form hydrogen gas. From these mechanism or reaction which will occur at anode and cathode, we see hydrogen gas is evolved at cathode, while carbon dioxide and alkane are formed at anode. Now, the remaining ion in the solution are sodium ion and hydroxide ion. These two ions combine with each other to form sodium hydroxide. We know that sodium hydroxide is basic in nature. So as reaction proceed, move further, the pH of solution gradually increases, because with basic character pH move on higher side of pH scale. Hence we can say pH of solution gradually increases. The mechanism of this reaction is as shown below. In the mechanism of this reaction, we will show there is the formation of alkane at cathode, which will occur by free radical mechanism. As we discussed above, acetate and ion or acetate ion will move towards cathode, where it will undergo oxidation by the method or way shown below. Acetate ion will lose one electron to form acetate free radical. This acetate free radical then decompose by the way shown in diagram to form methyl free radical and carbon dioxide. These methyl radical then couple with each other to form ethane. Limitation of this method. First limitation of this method is that only alkane with even number of carbon atom can be prepared by this method. Second, methane cannot be prepared by this method, because in this method alkane has even number of carbon atom, while methane has odd number of carbon atom, that is 1. So we cannot prepare methane by this method. Last limitation of this method is when we use a mixture of sodium or potassium salt of two different carboxylic acid to produce odd carbon number alkane, that is unsymmetrical alkane, then we will obtain a mixture of different type of alkane, which cannot be separated from each other, because these alkane have quite close melting point or boiling point to each other. In the last, we will take some questions what we are able to solve after watching or learning this video. Question number 1. How are alkane prepared by Core-House reaction? B. Wurtz reaction. Question number 2. Why is Wurtz reaction is not preferred for odd carbon alkane? Question number 3. How can you prepare methane and ethane from acetic acid? Question number 4. How can you prepare ethane from methane, propane from methane, ethane from ethene, methane from methane amine, 1-chlorobutane and 2-chlorobutane from methanol. Question number 5. Explain coal-based electrolytic method and decarboxylation of carboxylic acid. Thank you for watching this video.